Hello all, we're in group 15. My name is Jaimmy Cervantes.
Jerry Pico.
And my name is Adrian Arroyo, and today we're going to speak to you about the project for modeling of robots. First of all, mechanisms, what are they? They are devices that are used to set forces into certain arrangement of movements. Mechanisms consist of many things, various parts such as pulleys, gears, axles, levers, wheels, and screws. In a system of machinery, bodies which are connected are to be called links, and the connections between these links are called joints, or they're also called kinematic assemblies. Alright, so now we're going to speak about the history of mechanisms. First, let's start off with a mechanical engineer and German scientist named Franz Reuleaux. He was born September 30th, 1829, and he passed away August 20th, 1905. He was born in a town called Eichweiler, Germany, and he is very famous and he's known to be the father of kinematics. He is the scientist and individual that changed the mindset of thinking about mechanisms in a way of levers and pulleys to looking at them as rigid bodies that are links and joints. Links are all rigid bodies, so it makes it easier to analyze motion and to study velocities and accelerations, and the joints are what connect these rigid bodies together. He also portrayed mechanisms instead of links and joints, and he changed the mindset of all of the way we think about now.
Types of mechanisms. As you can see here on a linkage, it's very standard, where you have multiple links connected by joints between links. Now, links can consist of multiple single bars or solid sheet metal type solid links with also joints in the edges. Here you see a slider crank, which has a crank mechanism that revolves with a slider that stays on one axis without moving anywhere else. Furthering, we have cams, which have a follower riding on a cam that changes its pitch as it goes around the circle. Gears are used in power transmission to take power from one direction, step up or step down the torque and RPM, and output in a different direction.
In the first part of this project, we were assigned a 4-bar mechanism with certain values. What we needed to do, was use the values we have to calculate unknown joint velocities and accelerations, as well as displacements and angles of these different links. What we did was we used the vector analysis. We later derived to get velocity and derived again to get acceleration. And after calculating the data, we found the position trajectory of the mechanism. And then we also were able to use the SolidWorks database to create an adequate animation for this 4-bar linkage.
As you can see in this slide, here are the calculations we use for the 4-bar linkage. Here are the vector components for each link. We get the X and the Y. These are the position vectors which we use throughout our calculations. Once we get the position components, we derive this according to theta and R, and we get velocity components, and after velocity components, we derive again to get acceleration components. With this, we calculated everything by hand, and we got these results. After getting these results, we did it in SolidWorks, and we complied all the information, and everything was correct. As you can see here, here's the SolidWorks motion of the animation we did with the 4-bar. Here's the motion, and here's the double rocker, because the shortest one is at this link right here. You have this link, you have this link, and then the shortest one is on top. Hence, we figured out that this was a Grashof double rocker. There are many applications used for the 4-bar linkage throughout the world and nationwide and in everyday use, and one of the most commonly used is the windshield wipers in our automobiles, which uses that same double rocker motion, and that's why we concluded and we saw that the wiper method, its mechanism was related towards our SolidWorks motion. In this part of the project, we were supposed to create a slider crank mechanism which passes through certain points. You have the crank, the link, and the slider. We were supposed to create one which goes through certain points which were given to us. We were supposed to use geometrical calculations and analytical calculations. With that, we were able to create our slider mechanism which passed through all points.
In this part here, we analyzed our slider crank mechanism. We started initially on paper using just simple geometry and make sure we pass through all the points given. Initially, we have our crank with our origin here and our connecting links going to our slider point. As you can see here, as the crank revolves, the slider link moves back with the slider staying in one axis as the crank completes its full revolution. On this slide, you can see our initial calculations for our slider crank mechanism. Our initial calculations were done all by hand. We were tasked with finding a slider crank mechanism that would pass through 3 sets of points: A and B on set 1, A and B on set 2, and A and B on set 3. Our first set, as you can see here, was laid out in front of us. We took our crank, our connecting link, and our point C as our slider. A and B were our pre-described points we needed to pass through. We laid up our geometry, connected A and B together, point C to a slider, and began going to work. We found our angles, our lengths, and in general our passive motion by geometry and basic trigonometry. Moving on, we went to point B, and using the geometry from point A, we were able to calculate our angles, verify the motion, and from there move to point C. A and C are directly 180 degrees out of phase. Moving on to B was a little bit more difficult as we were at a weird angle, which we found later to be 60. Slider cranks are used in almost any situation. As seen here, a common piston in an engine is a slider crank mechanism. The crank being the rotating mass in the center of the engine, the connecting rod being the connecting link, and the slider being the piston. As you can see here, power is generated on the slider, pushing the connecting rod, moving the crank, effectively moving your wheels. Likewise, on a locomotive is another slider crank mechanism. As the wheel rotates, a crank rotates, moving the connecting link, moving a piston, which in a steam engine is powered by steam. But this is not all the applications. Conversely, in factories, these are also used for sorting, and on bikes, they're used for suspension. Applications for slider crank mechanisms are endless, and while here you only see 2, the possibilities will never end.
In this slide, we're going to present the animation which our slider crank mechanism was rotating at and passes through all the points. As you can see here, the link rotates fully and goes back along the axis, and it's along a slider. At each and every point, when it's flat, it passes through that first A1, B1, and then while it has at a certain angle, it passes to A2, B2, and then as it goes horizontally 180 degrees the other way, it passes through the last angle, A3, B3.
All right, so to conclude this presentation, we have discussed that analyzing both 4-bar and slider crank mechanisms, we can see different applications through these different linkages. We have also seen that analytical approach must be tailored to each and every situation in order to correctly analyze each different linkage for the correct answer. And last but not least, doing this project in a team environment helped us as a group in a great way to gain overall experience that will provide beneficial in future engineering endeavors, since there was a few issues in the project, but we worked together to get the job done and effectively be very productive.